Hello, welcome to our second video where we go through peer-reviewed journal publications and find some interesting things that we can help undergraduate organic chemistry students relate to real-world problems and understand why organic chemistry is important. And for everyone else, just some interesting new literature that we can review. So for this week, I chose the total synthesis of Setigerumine I, biosynthetic origins of the elusive racemic Papaveraceae, isoxazolidine alkaloids. So this is by Serna, and Setonen at the Department of Chemistry at Rice University. So it's a great paper, very interesting paper, which basically tries to uncover biosynthetic pathway using a synthetic method and backing up their findings with computational chemistry. So it basically touches all bases of theory and the biological mechanisms, and then the energetic barriers and different reaction specifics associated with it. So they get some really good results with this. I'm going to switch over to a scheme I made here. So here is this is the synthesis in the paper that they cover. So they start with Noscapine. We'll see this later. They do an N-oxidation using MCPBA, which ultimately leads to a cope elimination, and finally a domino CH oxidation. But first, I want to just discuss some of the botanical and biological origins of these compounds. So as we see here, this is the opium poppy, pretty common poppy that people have seen on TV or media or anything. You know, it's where opium comes from, and the scientific name for this is Papaver somniferarum, which means in Latin the sleep-bringing poppy. And this is a very important plant historically for mankind because it essentially changed warfare as we know it, because people could administer a pain medication to soldiers on the battlefield, and those soldiers who were trying to get a good night's sleep for the next day and for the next battle could sleep well, while all the other injured soldiers were not screaming in pain. So it really changed warfare, and obviously it's very important for medical usage, for post-operation, for extreme pain, and all the other compounds from it can be used to treat anything ranging from a cough to diarrhea and extreme pain, and many other different types of compounds come from this, such as codeine, morphine, and they can make derivatives such as oxycodone and heroin and all these other compounds that are used for medical purposes. So below we see the California poppy. This is this poppy right here. It's a very interesting poppy, contains a lot of cool compounds, and then the common poppy, which most people are familiar with right here. So this is a good filler plant for a lot of gardens. It's very commonly seen everywhere, and it has a lot of cool compounds as well. So the scientific name for the common poppy is Papaveraceae, and it contains this compound rohidine right here. And there's a lot of other plants and botanicals that contain a lot of these similar compounds, but namely the Papaveraceae family, which is the poppy family. So this first compound, sanguinarine, if applied topically, can cause some different types of sores, and it's not good. But the point is the structure of these. So californidine has a very strange structure. As we see, rohidine has a very strange structure, and coridine has a similar structure to that of morphine, if we can imagine connecting this bridge right here. The point of all this is just to show that the similarities in structures between these compounds and the potential biosynthetic pathways that the botanicals use to make these different compounds with different functions, and relate that back to this publication. So in the publication, they use Noscapine, which is a minor alkaloid isolated from the Papaver somniferarum, opium poppy, and they're able to produce this compound that has been isolated only a select few times with a really quick 3-step synthesis. And if we compare the compound Setigerumine I, which they synthesize, we can see it has the similar structure as all these compounds below. So it's very interesting. All right, so getting into this publication, we see the overall synthetic scheme that they go through using Noscapine, which is a commercially available starting material in a 3-step synthesis, which is an N-oxidation, co-elimination, and domino CH oxidation to get Setigerumine I. And for this video, we're just going to be focusing on Setigerumine I. So going down to the first figure, we see the structures of Setigerumine I right here. First isolated in 2013 from Papaver Setigerum. Dactyl icapnosine 2, which is isolated in 1995. And this dactyl icapnosine, which is more of a dimeric structure, very complicated, southern-northern unit. We're not going to be focusing on that for the scope of this, just these two compounds right here. They're hard to say as it is. So they basically have unknown biosynthetic origins, but in this paper, they seek to elucidate the biosynthetic pathway or potential biosynthetic pathway, which is really genius about this. So first, they start with Noscapine or beta hydrastine. So if you can imagine this R group can be a methoxy, it'd be Noscapine. If it's hydrogen, it is beta hydrastine. And these are the important part is these are commercially available starting materials. Now you can imagine they do an initial oxidation they use NCQVA. We'll see in a second. And further oxidation leads to a nitrone dipole, which then allows a subsequent co-elimination to occur, which they find happens very readily. And once this co-elimination occurs, we can break this ring open right here. And then we can form our spirocyclic compounds that we want to. So our Setigerumine and dactyl icapnosine. Now, the important thing is in this overall scheme for the biomimetic purposes, they want to connect to this this C2 position right here. And what they do is they try to look at the energy barrier of the favorability of connecting this versus connecting this methyl group, which could also happen. And so that's a concern we'll see in a second. So essentially they create this nitrone dipole for the further oxidation, which then does a 1,3 dipolar cycloaddition to get our products. And we can go further to make our compound 3, dactyl icapnosine. Going to the next figure to actually cover this synthetic works, what they do is they first start with Noscapine, and they do an oxidation reaction using CPBA and chloroform at 0 degrees Celsius. Now this oxidation creates an N-oxide, Noscapine N-oxide hydrochloride, and they do this in a fairly good yield, it's at 88% yield. And this is great. So they're off to a good start. The only problem is when they go to do the co-elimination, they find that they get their starting material back. So what they do is they partition this Noscapine N-oxide between chloroform and basic sodium hydroxide solution. And at room temperature, 21 hours, they get the co-elimination to proceed, which they then create the compound 6, which is their hydroxylamine intermediate. So the importance of the entire synthetic scheme right here is that in the P450 enzyme, this oxidation is known to occur, and in biological organisms, this is known to occur. They're just recreating that essentially using laboratory conditions. So biosynthetically, this happens. So they're trying to account for the presence of these previously mentioned compounds that they synthesize via biosynthetic processes. So this is just recreating the P450 oxidation. When we get to compound 6, they need to do an oxidative cycloaddition domino reaction. Now they first start out with mercury oxide, and they get fairly good yields of this compound. And so they create their nitrone dipole. And what is important with this is that there's competing reaction between the C2 right here and this N-methyl. So if they cause the oxidative cycle addition between the C2, they get their proposed compound Setigerumine I. But if they get the reaction between this nitrogen methoxy and the nitron methoxy, they get isosetigeramine, which is a compound that hasn't been isolated or accounted for in any biological species. So they actually get both of these. So they get 22% yield of the Setigerumine I and the 10% yield of the isosetigeramine. So they go back to the drawing board. Initially, they use mercury oxide, and they propose a method that would be, again, biosynthetic or biomimetic. Now, what they do is they employ copper 2 acetate, and they bubble air through a solution of copper 2 acetate and dichloromethane at room temperature to simulate biosynthetic conditions. So this is an enzymatic or biosynthetic reaction that can occur in organisms using copper, and therefore it is a plausible biosynthetic pathway. And they just recreate this geniusly in laboratory conditions by simply bubbling air through a solution with copper in it, which is really cool. And it undergoes this oxidative cycle addition domino reaction. So they have a few experimental concerns or curiosities that they want to look at, and that being the coelimination. So first, the coelimination usually proceeds under high temperatures in nonpolar solvents. In this case, they were able to accomplish this in DCM partition between after they freebase the Noscapine and oxide, they're able to carry out this coelimination at room temperature in dichloromethane instead of using something like toluene or benzene at 160 degrees Celsius. So they have a really facile coelimination, and these are not very common. Likewise, with the second major reaction, the oxidative cycloaddition domino reaction, they have this proceed at room temperature, which is also not very common. So why does this occur? And the researchers go into this. So going down, this just covers what we just talked about, where they use copper. Then they do computational chemistry to elucidate why this reaction occurs so easily. So in this figure right here, they have the Noscapine and oxide, and what they realize is that once they break open that initial ring and form their Noscapine and oxide, they have a syn coplanar dihedral angle, and the transition state for the coelimination is very similar to the intermediate. So the activation energy isn't very high to get to that transition state to undergo the coelimination. And we can see that they have their energies, so about 16.1 kcal per mole for overall free energy, and the enthalpy is 16.5 kcal per mole for the Noscapine and oxide. So it doesn't really have to overcome significant rotational barriers to reach the required syn coplanar transition state, which is required for coelimination, which is great. So this explains why the coelimination was able to occur at such unconventional conditions, without heat, without a nonpolar solvent. And likewise, their 1,3-dipolar cycle addition forming the desired product, Setigerumine I, also occurs at room temperature. And they discuss this too, using computational chemistry. And they get a overall free energy barrier for the transition state of that second reaction at about between 19 and 17 kcal per mole, so within reason. And then they also talk about the other aspects of the interactions between the nucleophilic and electrophilic aspects of the molecule. And we see that when we form Setigerumine I, as they say here for the nitrone, the homoenol to LUMO +1 nitrone is plus 3.04 electron volts interaction energy, which is lower than the ultimate pairing arrangement homo 19 nitrone LUMO enol of plus 6.6 electron volts, Then they go to talk about the Setigerumine I, which is a compound that they isolated as a side product and it isn't observed in nature. And it has a much different reaction pathway described as an amphiphilic dipolar cycloaddition. I'm not going to get into that much, but it just shows that these very similar pathways can lead to much different results based on just small aspects of energetic. So to restate essentially what they want is that they wanted this C2 position to add and cyclize to form their spiral cyclic product of Setigerumine. And in this transition state, we can see that now. We see with the alternate potential for the N-methyl group to form a ring, we can see that here, and that can occur through these interactions, and that leads to the isosetigerumine, which is the undesired product, but ultimately needs to be accounted for. So this is actually a really great ingenious synthetic pathway that they go through, where they essentially propose a biosynthetic pathway which accounts for the presence of these compounds in nature and organisms, and they essentially just mimic the P450 oxidation using MCPPA and using a co-elimination, which is known from literature to occur in organisms, and then they can just easily create an aerobic oxidation cycloaddition domino reaction. Anyway, I hope everyone enjoyed this. This was a cool paper to go over for me. Please like, follow, subscribe on YouTube, and follow us on social media. And please leave a comment if anyone has any suggestions for future videos to put up. Thank you.